Building secure walls network segmentation. Network segmentation is a fundamental security practice. It involves dividing a network into smaller, isolated segments. This limits the impact of security breaches. Think of it as compartmentalizing a ship. If one compartment floods, the others remain dry. Segmentation allows for granular control over network traffic. This makes it harder for attackers to move laterally within a network. Each segment can have its own security policies and access controls. Segmentation is crucial for organizations of all sizes. It's even more important for those handling sensitive data. By implementing segmentation, organizations can significantly enhance their security posture. Network architecture. Centralized versus distributed. Centralized network architecture relies on a central server to manage and control all network resources. This model offers advantages like simplified management and easier implementation of security policies. However, it also presents a single point of failure. In contrast, distributed network architecture distributes resources across multiple nodes. This approach enhances redundancy and resilience. If one node fails, others can continue to operate. Choosing between centralized and distributed architecture depends on specific needs. Factors like security requirements, scalability, and budget play a role. VLANs, creating secure traffic lanes. Virtual local area networks, or VLANs, are a common method for network segmentation. They allow devices on different physical segments to communicate as if they were on the same one. This is achieved by tagging network traffic. VLANs enhance security by isolating traffic between different departments or user groups. For example, finance and HR departments can have separate VLANs. This prevents unauthorized access to sensitive information. VLANs improve network performance by reducing broadcast traffic. They also simplify network management by allowing for flexible device grouping. Centralized computing. Shrinking the target. Centralized computing, where data and applications reside on a central server, offers security advantages. It allows for centralized security controls and monitoring. This makes it easier to detect and respond to threats. By consolidating resources, centralized computing reduces the attack surface. There are fewer points of entry for attackers to exploit. This simplifies patching and vulnerability management. However, centralized computing requires robust security measures on the central server. Any compromise could have a significant impact. Section 5. Cloud security. Single-tenant versus multi-tenant. Cloud computing offers flexibility and scalability. However, it's crucial to understand the security implications of different cloud models. Single-tenant cloud environments dedicate resources to a single customer. This provides greater isolation and security. Multi-tenant environments share resources among multiple customers. While cost-effective, multi-tenancy requires robust security measures to prevent data breaches. Choosing the right cloud model depends on factors like security requirements, budget, and compliance needs. Section 6. Data integrity, the foundation of trust. Data integrity ensures that data remains accurate and unaltered during storage or transmission. It's a critical component of the CIA triad, which also includes confidentiality and availability. Checksums are a common method for verifying data integrity. These are unique values generated from data using mathematical functions. Any changes to the data will result in a different checksum. Maintaining data integrity is crucial for trust and reliability. Organizations must implement appropriate controls to ensure data accuracy and prevent unauthorized modifications. Section 7. Zero Trust Architecture. Assume breach, verify everything. Zero Trust Architecture, or ZTA, is a security framework that assumes no user or device can be trusted by default. It requires verification of every access request regardless of its origin. ZTA emphasizes microsegmentation, continuous monitoring, and the principle of least privilege. This limits the blast radius of potential breaches. ZTA is particularly beneficial for industries dealing with sensitive data such as healthcare and finance. It helps protect against both internal and external threats. Section 8. Access control. Who gets in and where? Access control mechanisms regulate who can access specific resources and what they can do with them. There are several access control models, each with its own strengths and weaknesses. Mandatory access control, or MAC. This model is centrally controlled and based on security clearances. It's often used in high-security environments. Role-based access control, or RBACC. Access is granted based on predefined roles and responsibilities within an organization. This simplifies access management. Discretionary access control, or DAC. Owners of resources have the discretion to grant or revoke access to others. This model is flexible but can be less secure. Rule-based access control. Access decisions are based on predefined rules and conditions such as time of day or device type. This provides granular control. Choosing the right access control model depends on the specific security requirements and the type of resources being protected. Section 9. Control and data planes, the brains and the brawn of ZTA. In a zero-trust network, the control plane and data plane work together to enforce security policies. The control plane is the brains of the network. It manages and distributes security policies. The data plane is the brawn of the network. It enforces policies and forwards traffic. This separation ensures that security policies are consistently applied. The control plane verifies user identities, devices, and applications before granting access. The data plane enforces policies at each access point.